The present paper proposes a calculation algorithm and method for optimizing electricity consumption for the railway traction system. We will go over the introduction, the calculation algorithm for determining the electricity demand for a railway section, an optimization method for electric railway traction, efficient electricity consumption for the electric railway traction system, and conclusions. Introduction. The energy efficiency of the railway transport consists in the design of a calculation algorithm to establish the electricity demand for each section of the railway, the implementation of an optimization measure, as well as the realization of more accurate consumption forecasts on hourly intervals for the railway electric traction. For the design of the calculation algorithm and the optimization method, the following aspects must be taken into account: the number of trains in circulation on the section, the section slope, the train speed, and the speed restrictions, factors that will substantially increase the electricity consumption required for electric traction. Speed restrictions are limitations of the speed of trains on distances over which it is not possible to ensure the safety of train traffic at the speed set in accordance with the travel book due to running defects. On a railway section, there may be several sections with restricted speed described by the following situations: braking until the restricted speed is reached, travel at a constant but reduced speed, and an acceleration at the exit from the restricted area until the set speed is reached. The higher the number and limit of speed restrictions, the higher the electricity consumption for towing trains on that section. The inclusion of the hourly electricity consumption on the railway section in the forecasted one eliminates the payment of the penalties perceived by the supplier to the traffic operators. In order to define a calculation algorithm for determining the electricity demand for a railway section, the railway section must first be defined as the distance measured in kilometers from the injection point of a supply feeder from an electric traction substation or ETS and the delimitation point of a feeder area of an adjacent ETS. The length of a railway section varies between 25 and 35 kilometers, and it is delimited at the ends by the neutral zones. Figure 1 shows the electricity supply scheme of the railway sections. The mathematical model of electricity consumption starts from the speed-time relationship, respectively from the distance-time relationship. The velocity-distance curve and the velocity-time curve is a diagram showing the instantaneous velocity of the train along the ordinate and the time along the abscissa. This represents the change in speed at different times after the train starts. In the speed-time curve, the distance traveled during the given time interval is given by the area between the curve and the abscissa. Acceleration and deceleration are also given by the slope at any point on the curve to the abscissa. Acceleration and deceleration are also given by the slope at any point on the curve to the abscissa. Figure 2 shows the speed-time relationship for a given train with the four distinct components: an acceleration period, a constant speed travel period, a coasting period during which the train travels inertially, and a braking period. The electricity consumed for towing the train over the period t1 can be calculated based on the linearized speed-time curve. During this period, the acceleration is constant and the gradient is positive. The electricity ET1 equals force times distance equals FT1 divided by 2 times Vm times T1, FT1 being the traction effort, being the effort exerted by the traction system during T1 due to acceleration, gravity, and tensile strength. Vm is the maximum speed. The positive sign indicates a positive slope that implies an upward movement, and the negative sign indicates a negative slope that implies a downward movement. The energy consumption from time t1 to t2 is denoted by ET2 and is given by the equation ET2 equals FT2 times Vm times t2. During constant speed, the acceleration a equals 0. Therefore, the energy consumption at constant speed is ET2 equals m times g times sinus of phi plus m times r, all of it times Vm times T2. The total energy consumption is ET1 plus ET2. It can also be calculated by the following formula: m times Vm multiplied by a plus g times sinus of phi plus r divided by 2 times T1 plus plus or minus g times sinus of phi plus r times T2. The equation represents the total consumption of electricity for towing a train on a railway section, where the positive sign represents the positive gradient and the negative sign represents the negative gradient. The capacity to ensure the necessary electricity for towing trains on the railway section is given by the short-circuit level of the power supply, the possibility to dynamically modify the supply scheme in accordance with the consumption on the section in real time, the level of control, supervision, and automation of the installations that serve the electric power supply system of the railway electric traction. The optimization of electricity consumption can be done in the following way. The total energy consumption equation defined in relation 6 is considered the function to be optimized according to certain constraints. The optimization of the electricity consumption for traction is done under the following two constraints. A. The maximum speed, or Vm, reached by the train does not exceed the specified value. B. The distance traveled by the train, or S, must be constant. For a mathematical point of view, the objective function of the optimal control problem is defined as follows. Minimum of Fx equals E equals m times V multiplied by a plus or minus g times sinus of phi plus r divided by 2 times T1 plus minus g, or sine of phi plus r times T2. Constraints can be defined mathematically as follows. A times T1 is smaller or equal than Vm, and S is equal to 0.5 times A times T1 squared plus A times T1 times T2. In order to calculate the total electricity consumption for traction, real values for the parameters of the equation, the basic equation, and the two constraints are entered in the MATLAB program. Using the conventional method of optimizing the MATLAB program, optimized values of the parameters corresponding to the region of the optimal consumption point are obtained. Table 1 shows the real input parameters and the optimized parameters resulting from running the MATLAB program. The implementation of the method of optimizing the electricity consumption for the railway traction can be done by implementing the Monitoring, Control and Data Acquisition System, or SCADA, the MATLAB program, which will offer the SCADA system optimal control values for the section, for the specific trains and section of the railway. Efficient electricity consumption for the electric rail traction system. The current way of billing electricity for railway traction at national level is the one by which the consumer, the national railway company, forecasts the hourly or daily or monthly consumption for each electric traction substation and transmits the forecast to the energy supplier company, and the supplier is entitled to charge penalties for forecast errors. The solution is to eliminate these additional costs, and it is offered by SCADA's ability to perform energy remote management, which involves the dynamic modification of the supply scheme of the railway sections depending on the real consumption. If at any time the forecasted consumption is exceeded at the level of one electric traction substation, the consumption can be compensated by modifying the power supply scheme of the section from the adjacent ETSs at which there is underconsumption. Figure 3 shows the electrical supply of the railway sections through the supply fuses of the ETSs controlled by the SCADA system. The process of streamlining the electricity consumption necessary for the railway electric traction through the SCADA system includes the permanent monitoring on each ETS of the forecasted or realized consumption by hours or days or months, creating and sending as accurate consumption forecasts as possible to the supplier for the following periods, based on the analysis of the real consumption values previously registered. Conclusions. The calculation algorithm for determining the electricity demand for railway traction specific to a railway section can be used as a design basis for the modernization of the railway traction system. The proposed optimization solution offers the minimization of the electricity consumption specific to each section of the railway, the efficiency of energy consumption by implementing remote management in the SCADA system, offers a reduction or even elimination of the penalties charged by the electricity supplier for not being included in the consumption forecast for an ETS for a certain time interval. The optimization with the help of the MATLAB program of the calculation algorithm for the electricity demand on the railway sections, together with the application of the remote control and remote management offered by SCADA, are necessary and viable measures for the efficiency of the railway electricity transport. Thank you for your attention.